All right. There it goes. So, yep, more factor label. So factor label isn't anything like specific to chemistry. It's a way of working problems. And it's the way you need to work problems in here. I understand there's ways of working the same problem, like with a ratio, and that all works, but you need to get this under your belt because the problems are going to become more difficult. And like I said, this method will give you assurance that you have the problem set up correctly. So, within the English system, I have a yardstick here. Actually, a meter stick, which is kind of like a yardstick. So yards, of course, 36 inches a yard is 3 feet, right? It's an exact relationship. We're going to talk about square yards. So if you have 1 yard squared, so that's 36 inches by 36 inches, okay? And you want to know how many square feet you have. Well, you could look at it, and this is kind of what you have. So we have a yard on both sides, 1 square yard. So, of course, this is a foot, a foot, a foot. So how many, and so this would be 1 square feet. So how many square feet do we have? 9. You can just look at it, it's 9. And we could get 9 square feet. It's like a magic trick. We could get 9 square feet if we take this, recognize this 1 yard is 3 feet. 1 yard is 3 feet. We take 3 feet times 3 feet and you get 9. 9. And then the units, feet times feet squared. So 9 feet squared. Well, we're going to kind of drag ourselves through this applying the factor label method. So yeah, 1 yard squared is 1 yard times 1 yard. And of course, each yard is 3 feet. So 9 feet squared. 9 feet squared is equal to 1 yard squared. So the only catch is we're going to use that equivalency statement, 1 yard is equal to 3 feet. We're going to use it twice, and here's what it looks like. My pen's working, I think. It wasn't a little bit ago. So to work this problem, if basically I'm going to convert 1 yard squared to question mark feet squared. That's what I'm after. That's what we're trying to do. So if I go ahead and make my second term 3 feet over 1 yard, what units, if I stop there, what units don't I have? So let's see, one of these would cancel with this. If I stop there, I would have units of yard feet. If I introduce one more term, and you'll probably see, instead of the multiplication, I'll probably just kind of put these with parentheses around each term. Now, my yards squared cancel with these 2 yards in the denominator. Yards squared in the numerator cancel with the 2 yards in the denominator. And we're left with units of feet in the numerator. And by golly, if we take 3 times 3, of course we get 9. And you're back to the 9 feet squared. Okay, that's it. But we won't always have a nice little picture like we had. Notice that these, I'm going back and forth, I'm sorry, but these 2 terms, we could nest them together, and we could take that, since they're identical, we could say that quantity squared. So in other words, for this little conversion, we could have said 1 yard squared, okay, and then my yard squareds would cancel. One of the things I'm going to emphasize, if you do this quantity raised to a power, you have to take that power through. The power through the numbers in the numerator and denominator, the power through the units in the numerator and denominator. So yeah, that squared would make these yards squared cancel. We take that square into the 3, that gives us 3 squared is 9. We take that square into the feet, that gives us feet squared. Okay, so 9 feet squared. And by little, we're going to kind of look at it closer here with looking not with like area for like square, length square, and we're going to be looking at volume here in a minute. But just be careful. You can go ahead and say I need to take this times itself twice, And that's exactly what you're doing, but make sure that that square applies throughout. So don't let that catch you. So like I said, it's not, we don't care as much about area in physical science as we do volume. Okay, definitely when we get rolling with chemistry, volume's a player. So what does that look like? Well, here's a giant Rubik's Cube. This makes me giggle. So we're gonna say that it's 1 yard on all dimensions. What a humongous Rubik's Cube. It's been so long and I can only do it if like I have the directions and cheats, right? But anybody here? It's an old person's thing. But that's one type of Rubik's Cube, and you actually have to kind of move the little. So we have 1 yard squared, and the question we're going to actually answer is 1 yard squared, is equal to question mark feet squared. So what do you think the answer is? If each of these cubes is 1 foot squared, how many cubes do we have? How many cubes do we have on one layer? 9. How many layers do we have? 3. I'm liking 27. And 27 is the answer. And if you're a spatial person, you can't always in chemistry say, well, but that's it, 27 square feet. Square, I'm sorry, cube. Oh, please let me do that, sorry. Drat. Sorry, 1 yard cubed is equal to actually 27 feet cubed, final answer. So let's kind of pick it apart and see what that would look like. Well, we know from the kind of flattened out equivalency statement, we know 1 yard is exactly equal to 3 feet. So by golly, we know with an equivalency statement, we know you can make 2 ratios and use whichever one is to your advantage to make the units cancel. So we're going to go ahead and put 3 feet over 1 yard, and we're going to cube it. Okay. Just keep in mind that what that raised to the 3rd power means itself times itself 3 times. And so what is 3 cubed? 27. Yeah, 3 cubed is 27. So don't let that kind of catch you. Sometimes I'll work with students and they're like, well, I just already knew that. And I'm like, really? I didn't. I knew this relationship and I can take a cube through, but I don't know that off the top of my head. But you should know this. All right, so this bit about algebra, we know that if we divide by the same thing on both sides of an equality, simple equality like this, we know it's fair game. Also, if we raise both sides to the same power, that's also fair game. So nothing probably earth-shattering about that. So let's work a few problems. Yeah, and this is one where I couldn't just picture it. We're going to take cubic inches, where, you can see an inch here. So think of a cubic inch, and we're going to bring it up to cubic feet. So here's a foot. So cubic inches to cubic foot. Or at the top of your head, what do you think? If I'm converting 22 cubic inches, do you think that, how many people think that that will be more, here's 12, more cubic feet? Or than 22? How people think it'll be less than 22 cubic feet? Yeah, you should have less than 22 cubic feet. Less than 22, if you have 22 cubic inches, it should be less than 22 when you're from feet. That's another thing about problems, is does it make sense? Does it seem reasonable? All right, so in this case, one of the things you need to memorize is the relationship between inches and feet. What is the relationship? 12 inches, exactly. So I know I kind of put, well, if you want to look at it this way, you guys told me 12 inches? 12 inches is exactly equal to 1 foot, exactly. And since we're dealing with cubic inches, I'm going to cube the inch side, and that means I need to cube the foot side, and that's perfect. That's the game plan. Our first term, like we've been talking, is going to be the thing we want to convert. And usually I would put this over 1. I'm going to show you some options, how you think about it. I can't remember what my first option is. What I like to do is, because the cube thing kind of confuses me sometimes, I will literally put 1 foot over 12 inches, 1 foot over 12 inches, 1 foot over 12 inches, just so I know that I got my 12 basically raised to the 3rd power cube. This time you can see I just put 1 foot over 12 inches, quantity, the whole thing, cubed. Okay. So as I have it set up, inches cubed will cancel, be left with feet cubed. That's it. Does the way I round it make sense? Why did I get, how many sig figs are in my answer? Fingers. Everybody has fingers. Yep. I have 3 sig figs in my answer. Why didn't I do 2? Because that's exact. Yep, so 3 sig figs. Exactly. Then I have some slides to kind of remind you that that quantity raised to the 3rd power means itself times itself 3 times. All right, well, let's go ahead and do something that was within the English system. Let's go ahead and cross the imperial bridge. In this case, we're going from English units to metric units. Okay? Be like, I have no idea. Well, with regard to length, what was the relationship? I'll put inches here equals blank centimeters here. You have to memorize it. 2.54. Yeah, 2.54. Exactly. 1 inch is exactly equal to 2.54 centimeters. Now, if you find yourself doing 1 centimeter is exactly equal to 2.54 inches, you're in good shape because I've done that before. But concentrate and get it right. Okay, so centimeters are smaller. Centimeters are smaller. Cool. All right. Well, do you see if I can go from inches cubed to centimeters cubed? I can't. We haven't talked about 1 centimeters cubed. You can't really get directly to liters, but we can get from centimeters cubed to milliliters. What's the relationship between those, centimeters cubed and milliliters?
1 centimeter cubed.
1. Exactly. And then how are we going to get from milliliters to liters? 1,000. Yep. So here's kind of what the game plan is. We are going to go from inches cubed to centimeters cubed using the 2.54. Specifically, 1 inch is exactly equal to 2.54 centimeters, and we're going to cube it. And then you told me we can get from centimeters to milliliters with this 1-to-1 relationship. So centimeters cubed. Give centimeters cubed to milliliters with this relationship. 1 centimeter cubed is exactly equal to 1 milliliter. And then we can get from milliliters to liters, you told me, by a factor of 1,000. So remember, there are more milliliters. There are lots of milliliters in 1 liter. So 1,000 milliliters is equal to 1 liter exactly.
Is that like 10 to the 3rd equals 1?
Yes, that could be 10 to the 3rd. 1 times 10 to the 3rd, same thing for 1,000. But you could go either way though because it's exact. So, all right, let's string them up. What's my first term going to be? The thing I want to convert.
25.0.
It's going to be that. It's going to be 25.0. I couldn't remember what it was. Thank you. We 25.0. Don't forget the units, inches cubed, because that tells us what we will need to string up next. Put it over 1. Now I'm ready to convert from inches cubed to centimeters cubed. So notice again, I sometimes expand this, write it down 3 times, but if we just go with 2.54 centimeters divided by 1 inch quantity cubed, that will get our inches cubed to cancel. Those centimeters cubed. Then what do we do next? We want to cancel centimeters cubed. Yep, 1 milliliter over 1 centimeter cubed. Okay. Now we want to go to liters. So what does that last term look like? Yeah, don't worry about this stuff. This is just. So now I want to go liters. So what do we put as our last term?
1 liter of 1,000 milliliters.
Yep, 1 liter of 1,000 milliliters. So inches cubed have canceled, centimeters cubed have canceled, milliliters have canceled. The numbers we need to deal with now, I got 25.0, I got 2.54 cubed, and then that's in the numerator. In the denominator, I have 1,000. How many sig figs? Fingers. Right, 3. 3 sig figs. So so this is exciting. For 3 sig figs, I need to use one of those trailing zeros after the decimal to show 3 sig figs. Okay, so 3 sig figs. Okay? We good with that? Okay, so this part will be due Friday. I was going to say Monday, but no, it's Friday. And actually, I think we'll be able to get to the next part too. Any questions? It's all factor label. I haven't been fishing like I want to go, like at all this season, but I'd like to fish when I have the chance. And my mom got me a cup that says, I don't know what the question is, but the answer is fishing. Wasn't that sweet? So my thing to you guys is, I don't know what the question is, but the answer is factor label. So anyway, so this actually, I mentioned part 7 when we went through your calculations that's associated with the lab that you did last week. And so this finally is where we're going to be taking density. When we talk about density, it's just a ratio of mass to volume. Density, you basically take a blob like you did in lab, you get its mass, you get its volume, and you divide. So we can use density actually as a conversion factor to go back and forth between mass and volume. You can also use mass percent also as a conversion factor. So if you think of density as like a physical property of something, density is it's a physical property of that wooden block you measure. Density is a physical property of water. Granted, that physical property can vary at different temperatures, but assuming the temperature stays the same, you know what an object's ratio of its mass to volume is.
So do we only get, we don't measure density directly?
Right. You don't measure it directly. You measure the 2 pieces that go into density, mass and volume, and then you divide out. So if you ever have a physical property like that and you're like, I think I'm supposed to use it in this problem, but I have no idea. Look at the units of the physical property. So if density is mass divided by volume, if you have density, you can use it to get from mass to volume. You can also use it to get from volume to mass. So the units here tell you how you can use it. I'll show you what that looks like. So we're going to pick on methanol, and at 20 degrees Celsius, it has a density of 0.792 grams per milliliter. Now the next slide I'm going to show you, and I call it unpacking, I think I might have mentioned this before, that G/ml, that's not going to work for us to use that as a property to work the problem. I'm going to unpack it as 0.792 grams divided by or over 1 milliliter. Okay, that's how I'm going to unpack it. So the 2 problems like we can do here is the first one, and sometimes I just jump right, I don't even read the sentence. So I have 242 milliliters and I have what is the mass. So this one is I'm going to go from volume to mass using that density. The next type of problem is I'm going to go from mass to volume using that same density. So here we go. This is my unpacking So there are a lot of properties out there, a lot of ratios, a lot of physical properties we can use as conversion factors. And in order to use them, you have to kind of get them, the units in the numerator, the units in the denominator. You have to tease out well, do you see where, and we would call this second one the inverse, right? The inverse of density is a great way to go, depending upon what units I need to cancel. We can flatten it out. That's a physical property of methanol. So let's work the first one, and it's consistent with what we've done with other problems. For problem number 1, we were going from volume to mass. I start with the thing we want to convert, which is 242 milliliters. And when we've been working factor label problems, we know that somewhere down the road we need milliliters to cancel. We want to be left with grams, so what number goes next? 0.792 or 0.792 grams over or divided by the ratio over 1 milliliter. And of course that is the density. Milliliters cancel. How many sig figs? Figures. I'm liking it. 3 sig figs. You got it. So 192. Just specifically, 192 is the number, and the units that didn't cancel were grams. So 192 grams. So see how you can kind of use the units that cancel as a check. So the second problem, we were given this grams, this mass, 50.0 grams. We're supposed to convert it to milliliters, or to volume anyway. So what can my second term do to have grams cancel, be left with milliliters? Yep, 1 milliliter on top, exactly. And it's the inverse, or the flip, of the density as it comes. So 1 milliliter over the 0.0792 grams, grams will cancel, be left with units of milliliters. How many sig figs? Yep, 3. I'm liking it. So those are both the density. And I got 63.1 milliliters. We're even going to get out early because I'm not going on to the next part. Any questions about this one? The other problem I want to work with is a percent problem. And this is where you may not have done the whole density out in your real life type of problem to go back and forth between mass and volume, but you probably have done percent problems out there in your real life. And it might be different than I'm going to show you. This is going to be hardcore factor label. And you might be like, Mrs. Snipes, why make it so complicated? Just because I can, and it gets you down the road. So I'm going to unpack this here in a minute. 7.2%. But we talked about what percent means, and you probably already have a sense for what percent means. It means percent means parts per 100. In this case, it means grams of a component per 100 grams of the mixture that component is in. Okay? So I'm going to go ahead and unpack it. You can go to the next slide. So 7.2% in this case. And I guess I'll go ahead and draw a picture because I probably would. I would probably put sucrose, and I would put, water, and we have the solution here just because I can. So 7.2% means that I have 7.2 grams of sucrose in 100 grams, exactly 100 grams of solution. SOL''N. So I'm hoping you can look at that and kind of get to that. A picture, it's optional. My beakers that's not a regular beaker. They get really messy. So I said, so this is a physical property of this solution. Could they made it sweeter? Yeah. Could they made it less sweet? Yeah. So if we look at the units, we can go back and forth between grams of sucrose and grams of solution. That's our ticket to use this to get back and forth. So here's our 2 questions. How many grams of sucrose are there in 65 grams of solution? And then a follow-up question with the same solution is, what is the mass of the solution